This is another video that is continuing to go over the 2015 release questions for the chemistry SOL to have you review some of the things that are most important to understand. Consider any set of three adjacent elements in the same period on the periodic table. For which characteristic is the average for the three elements always equal to the value of the middle element? So this is one of those ones you have to really know what you're talking about. It says same period, so we know that period is the row. So those are those things. And if you were to take the average of any three adjacent, this requires a little bit of other terminology to remember. Adjacent just means next to each other. So if you take three elements that are adjacent to each other, and you take the average of particular information value about them, it will always be equal to the middle one. Let's try a couple of things. Let's try nitrogen, oxygen, fluorine. So you've got nitrogen, oxygen, and fluorine. The atomic number for nitrogen is 7, oxygen 8, fluorine 9. The average of 7, 8, and 9 is 8. Okay, and that is for atomic number. Let's try something else. Suppose that we had the elements phosphorus, sulfur, and chlorine. If we took the average of their atomic numbers, 15, 16, and 17, we would get 16 as our average. But if we took the average of their molar masses, or their atomic masses, then we would not necessarily get 16. The only number that is exactly and always equal would be the atomic number. This is one of those questions you have to just really think about it, and there's really no trick other than taking it one step at a time and thinking about the information presented to you. A substance has a molecular formula of C8H10N4O2. The empirical formula is, remember that the empirical formula is simply the molecular formula with lowest whole number ratios for them all. Let's think about glucose. Glucose is C6H12O6. That is the molecular formula, because that shows us the actual number of atoms in a molecule of glucose. But the empirical formula for glucose would be CH2O, because if you divide each number by the smallest number, you get a ratio. 6 over 6 is 1. 12 over 6 is 2. 6 over 6 is 1. So the empirical formula, EMP form, is basically the ratio of atoms to their lowest whole number. So think about a house party. You got a house party with lots of people in it. Parents went away for the weekend, and you invited a bunch of people over to your house without their permission. Shame on you. There were 30 boys, and there were 50 girls. The ratio, the number of people at the party would be like the molecular formula. There were 80 people at the party, 30 boys, 50 girls. But the ratio of boys to girls would be 3 over 5. So the formula for your house party, as far as this molecular formula, would be B30, G50. That is your molecular formula for your house party. The actual ratio of boys to girls, or atoms in this case, the empirical formula, would be B3, G5. So how would you turn 8, 10, 4, and 2 into a lower whole number? Take the smallest number, divide by them. 8 over 2, 10 over 2, 4 over 2, and then our actual smallest number, 2. And you end up getting C4H5N2O. And that is all there is to empirical formula. This one is tricky because some people who kind of breeze through and weren't thinking about it are going to think that the empirical formula is just an accounting for all the atoms as far as which atoms are present, but you have to have the ratio to the lowest whole number. Create the formula for diboron trioxide. So on the updated chemistry SOLs, you have to do a little click and drag and interactive problems. This is a naming problem with a covalent, or you could also call it molecular, compound. Molecular covalent compounds, they can use prefixes. You can use prefixes like di and tri. Di means 2, tri means 3. In our formula, we have 2 boron, so it'll be B2, and we have 3 oxygen, so it'll be O3. How would you click and drag? Well, capitalization matters. You would click and drag capital B, and then 2, and then you would click and drag capital O, and then 3 for the trioxide. So your formula would be B2O3. What is the name for the compound Al(I3)? Aluminum is a metal, but it is not a transition metal. So because aluminum is not a transition metal, do not use Roman numerals. That means that you just have to think about what it is. Aluminum is always going to be 3 plus. But since it's not a transition metal, because it's always 3 plus, it's just aluminum. It's just literally aluminum. No need to put aluminum 3 because it is always 3. You may be tempted to put triiodide for that I3 that I somewhat covered up, but it is simply iodide. Because although iodide has a -1 charge, there are 3 of them. You do the switchy trick, and that's how you get your formula of aluminum iodide. Remember that you do not use tris for ionic compounds, and you also don't use Roman numerals for non-transition metals. So it's a little bit simpler even than it makes it seem. It is literally just aluminum iodide. I have no idea how many times I said literally, but it literally is just that, literally. This next one asks, how many moles of carbon dioxide are produced when reacting 6 moles of butane and excess oxygen? Finally, we have a stoichiometry problem. Remember that stoichiometry is where you have something that you're starting off with, I don't know, an amount of one thing. So we have moles of butane, which is C4H10. That's the stuff found in lighters. We have moles of butane. We're going to turn our moles of butane into, if you remember how stoichiometry works, sometimes you have to turn things into moles. We actually are already given 6 moles of butane. There's no need to turn, I don't know, 20 grams of butane into moles of butane. We are actually directly given moles of butane. This saves us a step. Matter of fact, another step is saved because we are solving for moles of carbon dioxide, so we don't have to turn it into liters or grams. We're going straight from moles of butane to moles of carbon dioxide. It says excess oxygen, so you know what excess means. Forget about it. So the molar ratio is given to us by the coefficients. We've got butane here. Ignore oxygen. I mean, it's there, but we don't need to care about it. Also ignore the water, because it's there, but we don't care about it. In this, we're going to take what we know, put it over 1, and keep it moving. 6 moles of butane, C4H10, over 1. I'm going to go from moles of butane, not to grams or liters because we actually are we have moles of our starting stuff, turn it right into moles of what we want to know, which is carbon dioxide. The molar ratio is going to come straight from the balanced equation. There's a 2 in front of butane. There is an 8 in front of carbon dioxide. 6 times 2 divided by 8 is the same as 6 times 4, and 6 times 4 is 24. So this is our answer right here. 24 moles of carbon dioxide would be produced if you had 6 moles of butane and a bunch of oxygen that wasn't going to run out. In more complex stoichiometry problems, you may be given something like grams of butane and go from grams of butane to moles of butane. And then moles of butane to moles of carbon dioxide. And maybe the problem would be like how many liters of carbon dioxide at STP, in which case you do this. That is the more complex one. We were actually only using this section of the stoichiometry. You could have gone from many different directions. You could have had, other things. But we were only given this, so this was actually a pretty simple problem. Just make sure you know how to do the more complex ones, where it's not just moles to moles, but more like grams to liters or liters to liters or something like that. Which structure represents a non-polar molecule? We talked about Vesper theory and polarity in great detail. So you have to really think about a couple of things. Hydrocarbons. Let's go back to this. Hydrocarbons, which are molecules with only C and H atoms in it, are nonpolar. Because the electronegativity difference between carbon and hydrogen is negligible, and molecules that have only carbon and hydrogen, known as hydrocarbons, not to be confused with carbohydrates, are nonpolar. So that kind of narrows it down a bit. But let's draw some dipole arrows as a nice review of the polarity unit. I believe this is formaldehyde. Formaldehyde has an imbalance of electrons. It is trigonoplanar. Electrons are going to hang out a lot more on the oxygen side than on the hydrogen side because the oxygen is electronegative. Hydrogens are considered to be partially positive. So this is definitely polar because it is uneven sharing of electrons. If you were to draw chloromethane in three-dimensional Vesper structure, doesn't matter where you put the chlorine, but this is a polar molecule because electrons are going to hang out more on the chlorine side because chlorine's electronegative. And then you have electropositive everywhere else. So because this is uneven, it is also polar. Ethanol is polar because there's an oxygen over here that is nothing to balance out with on the other side. So electrons are going to flow in this direction, and that is going to be polar. Ethanol, or water, ethanol, alcohol dissolves easily with water because water is also polar and they can do hydrogen bonding and are just polar in general. So anything that can do hydrogen bonding will likely be polar. Which structure represents nonpolar? The only one that makes sense is A, because it's only carbons and hydrogens, and we know that carbon-hydrogen bonds are nonpolar. Plus, it's pretty symmetrical. Using only one trial to collect data in an experiment, as you should remember from prior science classes, is bad because one trial could have an error. So let's think about this. Using only one trial makes it easier to determine a valid conclusion? No. It actually makes it harder because having one trial, something could have happened and your conclusion is much less valid. More trials is better. 3 is the standard minimum. 5, 7, something else above that is better. Reduces the percent error in the results. Irrelevant. The percent error is determined by the actual errors that present themselves. Causes the conclusion to be less reliable. That is true. We literally just said that more trials is better. Having just one trial makes it a much less reliable experiment and requires data with more significant figures? No. So effectively what you need to do is just go back to the basic scientific method, scientific investigation things that you've been talking about since 6th grade or even before. A common product of acid-base neutralization is acid-base neutralizations always produce two things. One thing it produces is water. The other thing it produces is a salt, which is basically a metal and a non-metal combined. That should be a negative sign. Let's take a look at an acid-base reaction example. If you have, this is a very generic example, you have some hydrochloric acid, aqueous. You mix it with some sodium hydroxide, aqueous. In a 1-to-1 ratio, what they will do is you get kind of like a double replacement reaction, a neutralization reaction, where your hydrogens, try that again, where your hydrogen gets with the hydroxide to create the water, HOH, H plus, OH minus, you get HOH. More likely see it as H2O. And then with that, you get your salt, which is NaNCl. And remember that the positively charged ion comes first, so that's going to be written as NaCl. Regardless of the order it is given in the problem, this is going to be your salt, and this is going to be your water. Almost for H2O again. And your water will be composed of the acid hydrogen ion and the base hydroxide ion combining. And then your salt will be the metal cation in the base and the non-metal anion in the acid for a generic common acid-base reaction. There are many more complex ones that have different things going on, but this is what you understand. Water is a product because water is neutral. And salt would also be a product if it were asking that. Now let's think about some other things here, because this problem could say a common product of a combustion reaction is. Combustion reactions tend to form carbon dioxide and water. Combustion reactions also tend to require oxygen, but this is asking about acid and base, so water is our answer here. Here's a data table about the brightness of a light bulb where current is running through a certain solution of a certain pH. Based on the information provided, which solution is a base and a weak electrolyte? There's a couple things to think about here. Remember that an electrolyte is a compound, like a solute, that when dissolved in water, conduct electricity. So here's what an electrolyte would look like. Suppose I'm drawing out just a solution, and in this solution I've got ions floating around in this aqueous solution where the main component, of course, is water. I've got copper wires going in. Say I've got one going in this side, got another one going in this side. The copper wires are not actually touching. I've got a battery in here somewhere also, and this circuit is considered to be closed. I've got, say, a light bulb. This light bulb will either not light up if it's a non-electrolyte in this solution. It'll light up weakly or dimly if it's a weak electrolyte, and it'll light up brightly if it's a strong electrolyte. So how bright is this light bulb is our question here. It asks about a weak electrolyte. We know that a weak electrolyte will be dim because it's conducting electricity but not super great. So a dim light bulb. So we're looking for weak, which means you can cross out the bright light bulbs because those are considered to be strong electrolytes. So So these are going to be weak. And then the next piece of information that helps, and I'm going backwards for no particular reason, it says a base. Remember that bases have a pH of greater than 7. HClO is considered a weak electrolyte, but it's an acid. So we're going to cross that one out too. What does seem to fit the requirements is that CH3NH2 is a weak base. So with problems like these that seem like they have a bunch of information you feel like you've never learned, or you learn pieces of it and it's kind of fuzzy because it's the end of the semester, just take it one step at a time and look at what it's really asking you. It says on this particular one, what is the half-life of americium-242? This is mostly review from, honestly, earth science and even 8th grade as far as half-lives go. But the half-life is the amount of time it takes for half of the parent isotope to decay. So at time 0, you have 80 micrograms of americium-242. And I believe I'm pronouncing that right. I don't say it often, but I just have always said it americium. It sounds better than americarium. So americium-242, you have 80 micrograms to start. Micro is mu, g. 80 micrograms to start. And we want to see, well, if I have 80 to start off with, how long does it take to get to 40? 40 would represent a loss of half of the mass of the radioactive parent isotope. So we know that the mass gets cut in half. 1/2 the mass. But we want to know what is the amount of time it takes to do that. So T 1 subscript over 2 is called the half-life. It took 16 hours for half the mass to go away, and that is all you would put is 16 hours. Sometimes a half-life problem will give you the half-life itself, so knowing that the half-life is 16 hours, it may give you a chart and ask you to determine how much parent will remain after, say, 32 hours. You could look here and be like, well, half of half, which is a quarter, so it'd be 20. After 48 hours, it'd be half of a half of a half, which would be 10, and downward. I do not believe you'll be asked to use the actual half-life equation that involves logs and exponents to find something weird like at 51 hours, because that would require you to do more than just interpolate from a graph. I will do one more for this video, and then I believe I have enough to do 1 or 2 more videos for the end of it. 2 electrons are shared equally in bromine. What type of bond is represented between the bromine atoms in this Lewis structure? So the bromine atoms here both have the same electronegativity value. I don't know exactly what their electronegativity value is, but it's irrelevant because they are equal. They're actually equally sharing electrons. The word sharing means that it's a covalent bond, because they're both nonmetals. Non-metal, non-metal. So we can cross out ionic. They're clearly not metals either. Silly answers. But now we have to think about, well, we know it's covalent. Is it polar covalent or non-polar covalent? This would be considered a non-polar covalent bond because the electrons are equally shared. An example of a polar covalent bond would be like if you had carbon and oxygen and carbon monoxide. This would be considered a polar covalent bond because electrons are going to be flowing toward the oxygen side because it's more electronegative. If you were to put dipole arrows, partial charges, it'd be partially positive on the carbon side and partially negative over here. But because bromine is bromine and is equal on both sides of that single bond, it is considered to be non-polar covalent, not polar covalent.